happened?
Still green. Anybody else out there?
Can you check the mic? Let me give it up.
Okay, we're going to do a sound check here. Mike Cherma, can you speak up?
We are connected to audio. We're sharing our screen. He says, yes, still can hear you. We can hear you.
All right.
So.
All right, we're good. There, apologize for the we'll start from the top again. Welcome, everyone, for RITT Forum in December. Today's speaker is Tom Filiaggi from Meteorological Development Lab. By way of disclosure, I will mention that Tom works for me, so not exactly a partial host of the RITT Forum today, but nonetheless, Tom's going to talk about, he came on within this year, I believe, his first talk about the lightning jump.
There was an earlier RITT. I forget what month it was.
Yeah. So Tom's been here before. With the
about a year ago.
About a year ago. This study was initiated about 2 years ago at the request of former OST director and Steve Goodman from NESDIS to look into the possibility of a lightning jump algorithm based on total lightning data as possibly something that could be implemented in weather service operations to address the false alarm, or reduce the number of false alarms that are associated with severe thunderstorm warnings and tornado warnings. This study, the 2-year study, was completed, and Tom's going to present the results. I would indicate, though, that the research is ongoing, and the folks, the principal investigators involved with this, are continuing to investigate. So, as per usual format, 30 minutes or so of presentation, and then we'll have Q&A. Please hold off on your questions for the 30-minute section. And the session is being recorded as well, so after it's complete, we'll upload that to the RITT Forum site, and you can download it and share it with your colleagues. So with that, Tom, take it away.
All right, thank you. I will just jump to the, well,
We have to move it around.
I was using the keyboard also.
Yeah.
I will be changing slides in a minute. There's that.
Right. Yeah, you should get it.
Okay, thank you. Oh, there it is. Okay, so, second, what is that?
Click on anywhere.
I am. It's not.
Click.
I am. It's not. It doesn't want to do it. The middle's done. Keyboard. Let me do that and do that and do that. There we go.
Okay.
Now it's working. Yeah. Okay, here's our quick little agenda. I'm going to go over who the primary team members are, give you a little review of what is meant by total lightning, and talk a little bit about what these lightning mapping arrays are, give a quick little summary of the previous research, why are we doing this, what the current project was trying to do, a little bit of analysis and results, and describing a little bit of the future work that could be done as well. Here's a list of some of the primary team members. You'll see that I was co-lead with Steve Goodman. Steve Goodman's associated with a lot of the GOES-R, the GLM. The principal investigators were Larry Carey from the University of Alabama, Huntsville, and Kristen Calhoun from the National Severe Storms Laboratory. But Seamus Cronus and Chris Schultz were also involved with a lot of the analysis, as well as a couple of other students, I believe, from the University of Alabama. But you'll see a number of organizations that are there, and they all contributed in some way or other, at the very least, to discussional elements, and at most to providing some examples of what visual displays might be used for lightning jump and total lightning in general. Next slide is talking about total lightning now, and this is a slide that I talked about last year, and I'll go over it again real quick. Usually, at least in the English display right now, when you talk about lightning data, you're talking about the NLDN, which is only cloud-to-ground lightning. So cloud-to-ground lightning display that most people are familiar with in the Weather Service is a single point which represents where the cloud-to-ground lightning stroke intersected the ground. But with total lightning, you have the opportunity to represent one lightning flash or stroke with multiple points of data, which would constitute one full flash. So you can have anywhere from maybe 10, 20, up to over 200 individual sources be identified with one lightning flash using the lightning mapping array sensors, and I'll talk about the sensors in just a minute. The cloud-to-ground lightning is what is most directly affecting the well-being of people, because that's where most of us are on the ground. But if you use total lightning, the idea is that you might gain more meteorological knowledge of what the storm is doing, which might aid in warning operations. The lightning mapping array is what was predominantly used in this study, and it uses a pretty simple tech about time of arrival and multilateration to locate the step charges. And multilateration is just basically triangulation with more than 3 points. An example of one network in northern Alabama is represented here, though the white image shows these green dots that are a number of these sensors and how they're linked network-wise. And the gray and black map represents approximately the confident domain of that sensor network. So you can think of an LMA domain as approximately the size of a state or a smallish state. The distribution of those sensors will affect that domain. If you cluster them tightly, the domain gets smaller. You spread them out, they get larger. But there are limits to that. The next slide, very quickly, the summary of the previous research. Back in 2007, Chris Schultz, who was a student, I believe still at Northern University of Alabama in Huntsville, started looking at some of these total lightning ideas and trying to figure out if the idea of total lightning could be useful to warning operations. And eventually, he kind of suggested that, hey, if we do this certain type of analysis, our probability of detection stays pretty consistent with what the Weather Service averages, but our false alarm ratio is much less than what the Weather Service averages. Now, granted, this study did not directly compare the national weather stats for these storms with the stats from the analysis of the same storms. It was just comparing to the National Weather Service average. But still, a false alarm ratio of 33%, that catches people's attention. Now, continuing the research, a couple of years later, Chris tried to provide a better population for his analysis. The previous one only had approximately 107 thunderstorms analyzed. And finally, in 2011, he had over 700 storms in his database. And the results were similar. You still had a reasonably high probability of detection, and the false alarm ratio was still very low. That gets a lot of people's attention. But it was acknowledged that these studies were very much manually quality controlled. There were a lot of things that Chris did, such as manually correcting for every storm track that was identified to make sure that it was sound. And obviously, we can't do that in operations. We don't have that luxury of time. So what would happen if you took out some of that automation? So the summary of the previous research very quickly was this idea of the 2 sigma lightning jump, the 2 standard deviation approach looked very promising. But as I just mentioned, they were manually quality controlled quite a bit. The comparison wasn't done for Weather Service using the stats from the same storms. It was a Weather Service average. And so how this approach fare in an operational environment. So the current project, which as Steve mentioned, was kind of started about a couple of years ago. The primary goal was to remove that burden of the manual intervention, to see how this approach fared without it. And secondary goals were to give a little bit of attention towards the storm tracking, which was a different algorithm being used for this. Previous studies used the Titan algorithm, I believe from NCAR, and what was used for this study was something called SegMotion, which has been developed at NSSL. And it's pretty flexible. It is different, though, and so some of its characteristics could have affected the results of this study. And of course, another secondary goal, which I mentioned last year's presentation as well, was, verification. How you go about verification can affect your results quite a bit. And the verification techniques that were used are not the best here, so what can we do to perhaps improve that and improve verification of severe weather analyses in general? Next slide, talking about the current project, and I show this to give you an idea about, one, what the tracking looks like and what LMA networks we're talking about. So in the bottom right, you see the black map with the little gray dots. Those represent the lightning mapping array networks that were used for this study. Predominantly, the Northern Alabama and Oklahoma and DC LMAs were used. Now for this study, excuse me, in previous studies, Chris did a lot of focusing on the Northern Alabama network because that was the one that was up the most, it was the most reliable, it was the most mature. But for this study, a lot of the weather that happened was in Oklahoma, and so it also shows a little bit of represents a different climatology. And in the upper right, it gives you another idea of what this SegMotion storm tracking does. It's basically a cluster analysis, so you don't have a consistent shape nor size of storms that are identified. You've got these clusters, these blobs. And the algorithm itself allows you to analyze these things in different scales, like small, medium, large. And for this type of an analysis, the median tended to work the best, and that's what you see here, these ideas of these storm clusters that are considered to be the same storm. Next slide, here's some of the analysis numbers. Even though this project started in gathering data for the severe weather and summer seasons of 2012, the data wasn't usable. There were some problems in the processing, and they weren't caught until afterwards, and time was not available to reprocess everything. So we decided to settle for just the data that was collected in 2013, which is basically April through August. And looking at that data, we had 131 storm days, over 3,400 tracked storm clusters. Nearly 600 of those clusters experienced lightning jumps, and we had approximately 675 storm reports recorded over the same time period. Now, those storm reports are the ones that would be found in basically from local storm reports, the LSR product the Weather Service generates. They were quality controlled. They weren't used in their raw preliminary form, but we also did not wait for storm data to collate them and quality control them in their normal fashion. So the results, a variational analysis was done to taking into consideration a number of variables, and so there's a range here that we'll talk about. Probability of detection was anywhere from 65 to about 80%, a little bit low. False alarm ratio was 75 to 85%, a little bit high compared to the previous studies. Lead time was on the order of 25 minutes, which is consistent with the previous studies. When we're talking about the lightning jump approach, there's a couple of important thresholds to look at. One is the sigma, and the other one is the lightning flash rate threshold. For this study, the best sigma was around 1.2 to 1.7. Previous studies called it 2. And the best threshold here was anywhere from 9 to 12 flashes per minute. In the previous study, 10 flashes per minute was used. That threshold was used as the storm needed to achieve that threshold before the lightning jump would even be evaluated. So the false alarm ratio values are much higher than previous studies. The previous studies had them down in the mid-30s. This study had them pretty much where a lot of other analyses from different hazard management approaches show it. The false alarm ratio is about 75 to 85%. Now, the principal investigator and the other analysts also did some calculations to figure out, well, if we did some things differently, or if we try to account for other things, how could we get the false alarm ratio? And taking all of those things into consideration, we figured out, well, perhaps the false alarm ratio could improve to 55 to 60% if we could account for things like storm tracking imperfections and low population, storm report degradation. If the severe weather is happening where people are not, you're less likely to hear about it. If we were to arbitrarily state that 50 flashes per minute is a proxy for severe weather, that could also help. And some of the methodologies, the verification methodologies in particular, if we changed it in certain ways, we could also get some improvement out of that. But even considering all those things, it's still significantly higher than the previous studies. Why would that be? My personal opinion is I don't know that we've got some really clear answers to that question. But ideas proposed were that the geography could be different and the climatology, like I mentioned a couple minutes ago. Previous studies focused on the Northern Alabama area predominantly, and this study ended up using Oklahoma. Different climatology. Could that have affected the results here? Also the population density. Oklahoma has a lot of farmland, fewer towns where lots of people gather, so that affected this even more than what was already analyzed for. Methodology had a couple of things. One thing to mention is, in the previous studies, because there was a lot of manual quality control, the manual steps taken were good steps, but is it feasible, does it make sense to just extract them and not adjust the rest of the methodology? Does that make sense? And perhaps not. We took out the manual steps, kept everything as best we could, but is that good enough? So one of the things that was done manually in the previous studies was to manage these storm tracks and extend them artificially, somewhat artificially, if they progressed out of the domain, for example, or at the edge of the domain. When they're looking for reports, there was an assumption that the storms would, of course, continue out of the domain. We don't know it for sure, but they were extended, and that could produce some different results. And the storm tracker itself, as I mentioned, the seg motion that was used for this, that came from NSSL, has different behaviors than the Titan algorithm from NCAR. How much do those differences in behavior, how much does that affect the results of the study? It could also be in the mix. We also had some data integrity problems, even though I mentioned with the 2012 data, there was problems with that, so that was excluded from this, but in the 2013 data, there were still some cases where the total lightning inexplicably seemed to drop below the cloud-to-ground lightning, which should be impossible if all the sensors are operating as they're supposed to. Only one case was noted of this. That the data was not scoured to find them all, but they found one, so how many were there and how much of an impact would that be? There could be still some problems with data transport, data processing. A number of things could have happened that could cause some of these dropouts. Future work. One of the big things that we wanted to include, or at least plan for, was, well, we already knew that verification was going to be a tough nut. It's one of the rough spots of these kinds of studies. Can we do it better? Well, in order to do it better, or to at least explore the methods of doing it better, we need a better report data set. And so while this lightning data was being processed and gathered, we were also making use of the SHAVE project, where they would get usually students from the college to make phone calls, actively make phone calls in storm areas to try to find all the storm reports and where the storm reports are happening and where they're not, to get a better geospatial distribution, or more accurate geospatial distribution of these reports. The idea being, if that data is better, the verification results will be better as well. Hasn't been done yet, and hopefully it will be done over the next year. And as I mentioned, that some of the methodologies used in the previous studies were questionable. There were other ideas about, well, maybe we could improve some of these and make them better or more representative of weather service operations. Can the methodologies be continued to be refined? Make them even closer to operations. There's an example I can give in a couple of minutes, and since I am finishing pretty much early, I'm going to move on to some images to give an idea that to exemplify some of the things that I'm talking about. So we'll revisit that. This is the last slide, but I have a couple more slides with pictures. But I want to make sure that this is here, so get your questions ready. But you can always email me with questions. We have a community in the VLab for total lightning issues, and there's also a list server that currently exists. Now, the next 3 slides I have are pictures that I can go to. And here's an example of a methodology that might be questionable. I'm not going to read all the stuff at the bottom, but you're welcome to. The picture at the top shows the LMA flash rate, number of flashes per, I think it's minute. The green triangles represent lightning jumps. The little darker colored boxes represent severe weather reports. And then the green lines, both solid and dashed, represent the time windows from a jump within which the severe weather report can be associated to that jump. One of the methodologies that was used was that in that first jump there, you see the line is solid. But within that solid line, you see, if you look closely, you see 2 severe weather reports underneath that line. That means that those reports are associated to that first jump. But lo and behold, we have a second jump a few minutes later. Now, even though that second jump contains both of those reports within its time window, it's considered a false alarm because those reports have already been associated to a previous jump. Now, is that valid? Does that make logical sense? Well, there are reasons for it and reasons against. But if we didn't do this, could that affect the results? It certainly would. To what degree? And I think the more time would be spent in looking at this kind of a situation. Some of these methodologies need to be revisited to figure out whether it is giving you a proper evaluation or not. Now, of course, if we go completely different with verification and try to improve it as best we can, and I know Craig has talked a lot about how we might be able to do that, this question here might become moot. There could be a completely different approach, hopefully better approach, that would eliminate this kind of a problem. Next picture shows one of these data dropouts. The dark blue line is the LNA flash rates. The dark red line is the NLDN, which is the cloud-to-ground lightning flash rate. And inexplicably, we had some really strong flash rates. They dropped below the cloud-to-ground. And the cloud-to-ground, the difference there is pretty significant. You're talking of a difference of perhaps 50 flashes per minute. That's huge. That's more than just, oh, maybe it was close. No, this is definitely something going on here. And again, this is one case that the analysts found. They did not scour the data to see how many there were. Hopefully that's another bit of analysis that can be done in the near future. And finally, the last image, this is what is meant by a variational analysis, where all of the, well, not all, but a range of sigmas and a range of flash rate thresholds are all analyzed to see where the best performance might be. The little pink dots represent the previous study's estimation of what would be best. That's the 2 sigma and the 10 flash rate approximately. It's hard to see this, but what you want to see is where if the lines bow, where they bow against each other, it might be the best that we can come up with. So the 210 is close, but some better might be a little bit less than 10 or around 10, maybe a little bit less than 2 sigma. This is the kind of analysis that was done to see what kind of things could be. You can ignore the whole scenario 1, scenario 2 thing. The details there aren't really important right now. But the analysts did put forth a lot of effort to try to cover a lot of variational ground. So I probably was talking a little too fast, but I think I'm done. I'll go back to the questions slide and see if we have any questions either in the room or online.
Okay, thank you very much, Tom. I'll let John. So if those on the line, if you have questions, please, you have 2 options to use the raise your hand feature to indicate you have a question, and we can unmute you so you can ask the question over the phone, or you can use the question and text it in to John, and he can read it out loud. Do we have anyone who wants to ask?
Yeah, Mike Johnson, who you can hear us, would like to ask a question, and I'll let him ask it by me reading it.
John or Mike, go ahead.
Yeah, I actually have a couple of questions, but I don't want to take up too much of your time. But it seems to me I was at the original Schultz briefing to Don Birchoff, and I thought another aspect, and I think you're alluding to it in this presentation, another aspect that was questioned back there then was in the north, Schultz concentrating on the northern Alabama area, that looked at a specific class of thunderstorms that are common, but not necessarily common across weather service areas. So there was a desire to look at different types of storms. So my question is, in this study, was there any attempt to classify the storm type?
Not yet. So the classification according to things like severe weather type or climatology has not yet been done.
But the population of storms analyzed, you were saying they're maybe dominated by Oklahoma, but there are from D.C. and northern Alabama?
Oh, yeah. They're distributed out. And here's the other thing. This study, the predominant, by far, the predominant severe weather type was hail, and an overwhelming majority of the hail cases were in Oklahoma. It just happened, that's just the way it was with the data that was found.
Okay.
But there is data from D.C., there is data from northern Alabama. I think those are the 3, even though there were other networks available to the study in 2012. I would have to go back and look at the details of the paper itself to see if what the number was from those other networks. The one in Oklahoma also kind of spread a little bit southwest Oklahoma and northern Texas as well.
Okay. Mike, go ahead with your other questions.
My other question is tangential. Is MDL working on an improved scan version that includes a lightning jump flag?
Well, right now there's a preliminary step to getting scan to recognize lightning from multiple data sources. And Pete Rohr's in the room here, and he can also talk about this, but there's an initiative out there called Total Lightning. So once we get our hands on good total lightning and get that data into AWIPS, then there's this possibility of providing lightning jump and doing other things, other data processing. We could even do storm tracking according to lightning data as opposed to reflectivity, or storm tracking using both of those data sets. There are ideas floating around and being written down of the things that we could do and the things that might have value to operations. What the plans are exactly, well, that might depend on what happens over the next few months as to what gets worked on as a project versus what stays an idea. Pete, do you want to say anything about that?
Yeah, we're trying to keep the product simple enough so that we get things in front of the forecasters sooner than later. It's kind of an initial implementation, point data, some gridded data, and then we'll start looking at the products that are associated more with the total lightning as opposed to the cloud ground lightning.
Okay.
An interesting one, Mike, that you bring up is the lightning jump, because we could have lightning versus time for cloud ground and total lightning for particular cells.
Right, Pete, and we've talked about this before, and my thoughts are kind of lightning jump is one additional signal that the forecaster looks at, and how do you correlate all those things? And so my thought was, put them all together.
But the one thing we emphasize from a National Weather Service perspective, operational perspective, is the fusion of the lightning data with radar and satellite information, just like a forecaster would at a station.
Right. And so to reiterate what Pete said was the first step is, the hope is to, whatever lightning displays you see in AWIPS now, in regards to the cloud-to-ground lightning, the hope is that we can plug in total lightning and have those same types of displays with little effort. That would be the first step.
All right, thank you.
Do you have any other questions, Mike?
No, that's probably a side discussions, I guess.
All right, thanks. John, do we?
Let's see, Brian Maritsky?
Brian, go ahead.
Hi, this is Brian from Eastern Region. Question, you kind of answered our first question here in the room, which was about future plans. But I guess based on the research, does it seem like it's, is there an intent to do more research, or is there an intent to just start working on integrating this into SCAN or something like that before? What's the next steps or whatever in relation to this?
Yeah, this is Steve Smith. I'll answer first, and then Tom can maybe elaborate. But Steve Goodman, through the GOES-R program, is continuing to fund the research and the PIs that were involved in this study that's so far. So yes, research is continuing in that regard. And as Tom Filiaggi indicated, we are beginning to look at how we could modify SCAN or other parts of AWIPS to begin to position ourselves to use the total lightning data in effective ways.
Okay, so even though the research wasn't as outstanding as the previous research, or didn't show as much accuracy, it still seemed worthwhile to continue to look at this.
Right. The effort we're talking is not a high level of effort to modify AWIPS and SCAN to at least take in the data and begin. So it's fairly low risk. So we feel like we can go ahead and do that. In fact, the data are going to be arriving in AWIPS. So it's silly to buy the data and not provide them somehow. So, but the actual use of any particular lightning jump algorithm as some discriminator between issue a warning or not issue a warning, that's much further away, and that's certainly not justified by any of the research so far. the research results so far.
Okay, that's great. I have one more question, if possible.
Sure, go ahead.
Related to image number 1 that Tom showed. I was kind of just wondering, he showed a false alarm and then 2 hits, and I was just trying to understand how, what was the false alarm and what was the 2 hits, and why were there 2 hits and not 1, and why was there a false alarm if there was a hit, et cetera, et cetera.
Okay, you want to, can you give Tom the mouse again? Maybe
What?
to walk through with graphically?
Oh, geez. I mean, the reason why I included this image was to give an idea as to what methodology was used and how it could be done differently. To be honest with you, off the top of my head, I could not describe for you the full methodology that was used by the analysts. There was a lot of stuff going on. But I will try to go over this again. I'll just repeat what I said before. The idea is that these green triangles are, again, these are what is represented.
So just let me guide. So like the first green triangle is the first lightning jump in this, right? That's the first that the algorithm picked up.
That's right. That's the jump.
And the clock starts ticking on the window. Is that goal line? Okay. And so to the end there are 2 reports.
Right.
Okay. But only one of them counts as a hit. So that was
no. Those are both hits, but they're both hits to 1 jump.
Okay.
Now this jump here is considered a false alarm because it has no reports within its time window that have not already been assigned to.
Okay. I see.
Here.
All right.
And that's why it's dashed, because it's missed.
Did you follow that, Brian?
I think so. I think I'm understanding.
Yeah. Okay. So that seems pretty severe to not.
Well, the thing is, I think that the thinking was you could overinflate if you do it the other way. It's still not necessarily representative depending on how you do this. Now, the way they did it, again, they did it in steps. Once something was matched, they call it a matched cluster or something like that.
Pair?
And well, I don't know if I call that, but it's not a pair. It could be a match with multiple things.
Right.
And then they did something else with that. Excuse me. So I'm trying to remember the concern, the reason why they did that. They had a valid reason, but again, could it have been? Does it have to be one way or the other? Couldn't it be managed some way better? But then again, you're getting back into the whole manual QC of the data. We have to try to keep things automated to represent what we see in operations as best we can.
Okay, so continue on the third jump. It's got a hit, but that hit's already been associated with the first triangle.
That's right.
So it's also a false alarm.
Except this one down here. So I think this image here is probably a little bit confusing too, because this dashed line should probably be solid. It's a miss on that one, but here's one over here.
Yeah.
That it can be associated too. So this one goes with this one. Then we got another jump here, but that one's already taken into account, so that one is nothing. But then again, it ends here. Does that mean the storm cell is done, or should it have been carried out here? What if there was another report right out there outside after the cell was done being tracked? Does that count? Does it not?
Right.
So there's a little bit of that going on too. And so yeah, this is not such an easy and direct thing to think about. And this is one of the reasons why it became clear early on that verification was an ugly thing to have to tackle. There's so many different ways you can do it that would make your results pretty different.
And one struck just looking at this one example that you have like jumps and then you got super jumps, you know. And I mean, like the 2331, the one that's nearest to 20. I mean, that's the number of flashes is you know way greater than the previous jump. So, I mean, just you might say, well, maybe that one would be more likely to produce severe weather. I don't know.
Right. And you have this little valley here. Is this real? Is it a data drop?
Yeah.
You know, does it really matter? And keep in mind that the lightning jump, again, is basically a standard deviation of a magnitude of whatever the value that was used, which I believe was still 2 sigma, over the past, I believe, doing a 15-minute time window analysis. So they're looking at how is that rate changing over the, I think it's past 15 minutes. I have to think about that for a second. But bottom line is, that, yeah, you're right. This is not very clear signal.
No, that makes sense. The multiple jumps and stuff like that, again, it's one of the issues that you said with the original studies, how to differentiate. So, okay, thank you.
So this is Greg Stumpf, and I'm out here in Silver Spring with Tom. And we've been discussing the verification issues for quite some time now. And some of the things that we are hoping to explore here in the next year are different ways of treating both the severe weather reports and how we define what a warning is given the lightning jump information. So for the reports, one of the things that we have to bear in mind that those are just point samples in space and time of a continuous event. But we don't have a real easy way to define when the event began and when the event ended. So one of the things we're hoping to do is use enhanced verification database such as the SHAVE data, if anyone's familiar with that. It's very high resolution information on what fell from the storm, including the null reports when things are not severe. Or even using proxies from some of the radar algorithms that kind of give us an indication if a storm is severe or not for our reports. And then from the warning side, instead of treating each jump as an individual warning, we can kind of combine them and call what we say a period at which the storm should have been warned. So if you can see all four of those jumps, if we consider one jump to initiate a 45-minute warning, maybe we can say the subsequent 3 jumps extend the warning and continue it. So we've looked at a lot of different aspects of this. I wrote a summary of some of the different issues and things like that, and we're hoping to explore that stuff real soon.
Any other questions, John?
Yes, Mary, I think I can unmute her, so I'm going to just read her question. The first one is there a way to distinguish between severe weather types, hail, wind, and tornadoes?
Okay, so as I mentioned a little bit earlier, that this analysis did not separate out those severe weather types. How valuable the lightning jump is in regards to those different weather types is probably going to be different from type to type. It could be the case that lightning jumps are more valuable to the tornadic type as possible. This study did not go that far yet. So, but I believe that will be looked at.
And she also wants to know, does this study give encouragement to the GOES-R lightning detection for storm warning?
Can you say it one more time?
Sure. Does this study give encouragement to the GOES-R lightning detection for storm warning?
Well, as Steve mentioned, the funding for this originally came from the group that's looking at the GLM, the Geo Lightning Mapper, that's part of the GOES sensor array. That's what they want to know this about. Now, the sensor, the GLM, is a different type of sensor. It's a visual sensor, and its resolution is not as great as the LMA networks. The LMA networks are pretty good, but they're also local. They only cover small bits of ground. How could the lightning jump be applied to the data that comes from other data sources? That is not a quick yes or no answer. Using the LMA data, there was this idea of the 2 sigma and 10 flash thresholds. If we were to use a different data source, those would probably change. This idea of sources is something that is fairly well defined for LMAs, but it can be different depending on the sensor types. Now, for the satellite, I believe satellites are not looking at sources at all because it's visual. It's only flashes or strokes. That's a different data element. And so how would that apply to this? It's not quite clear, but it could still be attempted. And an evaluation could be done to see what kind of value that is. But again, the reason why this study is being done is that, well, if this is valid for LMA data, if it has value to operations, it probably would have value to operations as well using other data sources. It just might need to be used differently with either perhaps different thresholds.
This is Steve Smith. So one thing, I mean, kind of following up on this question, so you could say that the hopeful results were not achieved. You know, just even with you know, getting the 55–60% with including that's not good enough. It's certainly not 33% or something. So you know, I hate to say this, but you know, like we were thinking all along, that we use these data integrated with our radar data and our satellite data and other data. So to me, you almost have to go back to a case study type of approach where you look at, okay, well, there's a lightning jump detected in the lightning data. Now, does the radar data now contradict that? Does the satellite data confirm it? You know, and I don't think I've seen that kind of a study, either in a case study or anything else. So, you know, it seems like we've got to deconstruct these severe weather cases based on the different remotely sensed data sets we have, algorithmic or just looking at the data, and say, yeah, the satellite was showing this, or the radar was showing this, and the lightning was showing this, and only in these cases where they all aligned, and bingo, when you look at those, you know, you get a clear message.
That's kind of the concept we've been talking about, a controlled experiment, where we can take whatever forecasters will use right now to do warning position making, and then add to it the lightning jump information and see if that adds any value, if that increases the lead time, if that reduces the false alarm rates and things like that on the same cases, control case and an experimental case, which would have the lightning data added.
Because in many cases, you would expect the radar and lightning data to be in conflict.
Yeah.
So there's much more so than we've seen with cloud.
You'll probably also be encouraged because the analyst team has also come up with that same conclusion. They're starting to say, well, maybe we should, even though one of the desires was to make sure that you kept your population, your data population high, even valid, well, you know, what if we just go the other direction for those reasons, start doing it some individual cases to see how those compare. And so the analyst team did talk about that. I'm not really sure if they're including that in this next round of analysis or not. I hope they do.
Other questions, Sean?
Mike Johnson wanted to comment, and he can tell it himself. Mike, did you want to reiterate your comment?
Yeah, there was a question that talked about the relationship of the Northern Alabama site to the GLM, and that NASA Sport has been producing this pseudo GLM product off of their Northern Alabama site for some time now. So there is a direct way to make those comparisons.
Yeah, that's where they take the source data and produce a flash extent density product, which kind of mimics the optical flash that the satellite would sense.
Right. And uses the resolution from the GLM.
Yeah, yeah.
Other questions, Sean?
No.
Questions in the room? All right. If not,
Wait a minute.
okay.
I've got one.
Go ahead.
You said you changed the tracking algorithm and then said that might have influenced the results. I guess I wonder why you did that.
Well, the previous algorithms were seen to be just not very good. And to be honest with you, I haven't looked into the differences myself. I'm most familiar with the SCIT algorithm, which runs on the OpenRPGs currently. It's a full 3D analysis. The Titan algorithm is a little bit different. But the thing that was appealing about the SegMotion was that it was scalable. Because it wasn't clear, you know, thunderstorms, what is a thunderstorm, what is a discrete storm versus another discrete neighbor storm. Sometimes that is of a couple of kilometer scale, sometimes it is of a 10-kilometer scale, so the scale can vary. And so the idea was, well, you know, if we can apply this variable scale tracking system, we can see how that performs. We can run it on its low scale, on its medium scale, on its high scale. Now, the approach that was chosen, the medium, was a pretty obvious winner because the large had these really large blobs that covered too much area, and it was hard to associate any lightning to a single updraft or an updraft small system. And then on the other side, the small scale, we didn't have enough of a population to really work off of. The storms that were tracked had to be really concentrated to show up in the tracking analysis. Again, the reason to use that was of that scalability, I believe, and that it was already coded up into the system that was going to do the processing. It was already there. This was all processed on the NSSL WIDS 2 system. If they needed to use the Titan algorithm, they would have had to have written it in. And they figured, well, you know, and I think someone on the team had looked into it and found that the performance between the two should have been comparable, or that the cluster analysis was better. To what degree, I don't remember right now.
But the other, I guess, is more of a comment, and I think it goes towards what Steve was saying. It seems like with the tremendous difficulty of quote verification here, the numbers of POD and FAR that we're used to may not really apply at all. I mean, you know, you get a number, what does that mean compared to what we're used to? So it seems like somehow you have to get closer to what the operational verification is, or maybe a case study or something like that. I guess I'm just not sure what number coming out of something that's put together like this is going to mean.
Right, right. You're right. The attempt for this was to try to stay close to what the previous studies did. And the previous studies based their approach on being able to compare to the weather service numbers. So they're trying to do it in a similar way. If we go to an enhanced verification approach that does things fairly differently, you're right. Whatever numbers come out of that, what does that really mean? Are they even comparable to the old way of doing things, or does it have to stand on its own now? It's going to be a challenge to figure out, because we want this better approach to verification. Once we get it, how will we know it? You know, we can think about it methodologically, but the numbers that come out of it are going to have to be reinterpreted.
Any other questions?
I have one, Tom. I noticed you use a window of like 45 minutes, which seems rather broad, given that maybe an operational forecaster would want to be able to see the jump and then anticipate something more formally, like within 15 or 20 minutes. Is there any climatology on how frequently these jumps occur so that you could narrow your window?
It's not about the frequency. It's what they chose 45 minutes, I believe, because that was perhaps the average duration of a weather service warning.
For severe weather?
For severe weather. I believe that's why they chose that. Now, if you think meteorologically, and the whole idea of a pulse in a storm, it's not quite 45 minutes, but they can reanalyze and give it a 30-minute window or a 60-minute window. I think 60 minutes is too far. If you've got something 60 minutes out, how do you know it's associated to your pulse that happened at the beginning of that? That's an hour. That's a long time. 30 minutes is probably better. The 45-minute time window here was what was used in the previous studies, and that was continued into this. It's another one of those methodology issues that perhaps could be done differently. Of course, you do 30 minutes and your numbers change, and it looks not as stellar. And but yeah, you're right. I mean, there's also another decision there to be made about what's really representative conceptually.
Okay, thanks very much, Tom and the team. A very interesting study, and obviously these data is going to be flowing into our operations, so we do need to address how we can best use them. So thanks, everyone. Have safe and happy holidays, and we'll see you in the new year.